Title of the module: Unique Factorization Domains. Dear learners, in this session we are going to learn about unique factorization domain. Now let us start the study about those integral domains in which an analog of the fundamental theorem of arithmetic holds. First, the fundamental theorem of arithmetic is every integer greater than 1 is a prime or a product of primes. This product is unique except for the order in which the factors appear. That is, if n equals p1, p2 so on up to pr and n equals q1, q2 so on up to qs, where pi's and qi's are primes, then r equals s, and after renumbering the qi's, we have pi equal to qi for all I. Let us see some basic definitions here which will be useful to define unique factorization domain. The definition of associates is: elements a and b of an integral domain D are called associates if a equals ub, where u is a unit of D. In previous modules, we had learnt about irreducible ideals and polynomials. Similarly, here we are going to define irreducible element. The definition of irreducible element: a non-zero element A of an integral domain D is called an irreducible element if A is not a unit and whenever B, C belongs to D with A equals BC, then B or C is a unit. The definition of a prime element: a non-zero element A of an integral domain D is called a prime if A is not a unit and A divides BC implies A divides B or A divides C. Let us see some examples of associates, irreducible and prime elements. In Z, the units are 1 and -1, and each non-zero, non-unit element has two associates, namely itself and its negative. So, 5 and -5 are associates, 6 and -6 are associates, and so on. The irreducible elements and prime elements of Z are P and -P, where P is prime. Next, consider the polynomial ring Z of x. Units in Z of x are precisely f of x equals 1 and f of x equals -1. The irreducible polynomials of degree 0 over Z are precisely those of the form f of x equals p and f of x equals -p, where p is a prime. All irreducible polynomials are irreducible elements as well as prime elements of Z of x. In Q of x, the units are the non-zero constant polynomials. The associates of a non-zero constant polynomial f of x are the polynomials of the form a f of x, where a belongs to q set minus 0. So, x squared plus 2 is associate to 3x squared plus 6, 1/2 x squared plus 1, and so on. Finally, we come to the main definition, which is the definition of unique factorization domain. Unique factorization domain, or UFD, can be defined as: an integral domain is a unique factorization domain if every non-zero element of D that is not a unit can be written as a product of irreducibles of D. The factorization into irreducibles is unique up to associates and the order in which the factors appear. Let us see some examples of UFD. Z, or the set of integers, is a UFD by fundamental theorem of arithmetic. Every field is a UFD, or unique factorization domain. In a field F, every non-zero x belonging to F is a unit element. So, there are no irreducible elements. Therefore, the factorization of A is just A, a unit, empty product, or irreducibles, and this is clearly unique. The set of Gaussian integers Z of I equals the set of all A plus IB such that A, B belongs to R is a unique factorization domain. Finally, Z of root -2 is also a unique factorization domain. Next, we shall see some more definitions. Definition of content of a polynomial and primitive polynomial. The content of a non-zero polynomial a n x n plus a n minus 1 x bar n minus 1 and so on up to a naught, where the ai's are integers, is the greatest common divisor of the integers a n minus 1 and so on up to a naught. A primitive polynomial is an element of z of x with content 1. The next result will show you that the product of two primitive polynomials is again primitive in d of x, which is named as Gauss's lemma. Gauss's lemma underlies all the theory of factorization and greatest common divisors of such polynomials. It states that, let's see Gauss's lemma, let D be a unique factorization domain and let f of x and g of x be primitive polynomials in d of x. Then f of x times g of x is primitive. The proof: let f of x equals summation I equal to 0 to m ai x bar I and g of x equals summation I equal to 0 to n bi x bar I. Suppose that p is a prime dividing the coefficients of f of x, g of x. Let r be the smallest integer such that p does not divide ar and s be the smallest integer such that p does not divide bs. The coefficient of x bar r plus s in f of x, g of x is c r plus s, which equals a naught br plus s plus a1 br plus s minus 1 plus so on up to a r plus s minus 1 b1 plus a r plus s b naught. Since p divides a naught a1 so on up to a r minus 1 and b naught b1 so on up to bs minus 1, p divides every term of c r plus s except for the term a r bs. However, since p divides c r plus s, either p divides a r or p divides bs. But this is impossible. So, let us now see a lemma based on the content of the polynomial. Lemma: let D be a unique factorization domain and let p of x and q of x be in d of x. Then, the content of p of x, q of x is equal to the product of the contents of p of x and q of x. The proof: let p of x equal to c times p1 of x and q of x equal to d times q1 of x, where c and d are the contents of p of x and q of x respectively. Then p1 of x and q1 of x are primitive. We can write p of x times q of x is equal to c times d times p1 of x times q1 of x. Since p1 of x, q1 of x is primitive, the content of p of x and q of x must be CD. In this theorem, we will discuss about the relation between irreducibles and prime elements. The theorem is, in a unique factorization domain, every irreducible element is prime. So, we shall now do the proof. Let D be a unique factorization domain and let P belonging to D be an irreducible element. Now, our aim is to prove that this P belonging to D is a prime element. So, in order to prove that it is prime, let us assume that P divides AB for some A comma B belonging to D. So, let us consider the trivial cases first. Suppose A is equal to 0, then obviously P will divide A, and if B is equal to 0, then P will divide B. And in both cases, we have proved that if P divides AB, then P divides either A or P divides B. So, for this trivial case, it holds true. Now, let us consider another case. Suppose A is a unit, then P divides B. If B is a unit, then P divides A. How is this possible? Because if A is a unit, then it has an inverse. So, when we are dividing P divides AB, then A can be written as a product of itself as its inverse, and then when in that case they get cancelled and you are left with only B, and therefore P will divide B, because if P divides AB, then P should divide either A or P should either divide B. And the same way, if B is a unit, also B can be written as a product of itself and its inverse, and therefore you are left with only A, and therefore you will get P divides A. So, these two cases we have shown that if P divides AB, then P divides A and P divides B. Now that we have considered the trivial cases, let's go on to the non-trivial one. Let us assume that A and B are non-zero, non-unit elements. Since P divides AB, then AB can be written as a product of the prime number P as well as some factor C for some C belonging to D. Then let D is equal to PC, which is equal to AB. So, we are only just assuming that this value is equal to some D. Then from this we can say that D is a non-unit, because if A is a non-unit and B is a non-unit, then AB is also a non-unit, and therefore D, which can be written as the product of AB, cannot be a unit. Therefore, D is a non-unit. Suppose C is a unit. Now, we are left with only P and C here. We know P is a prime number and C we do not know, but let us assume that C is a unit here. Then, since P divides AB, AB is equal to PC. So, we know that AB can be written as a product of P and another term. So, AB is equal to PC, and this C is in this C is an element in D. Now, let D be any value, that is D is equal to both PC and AB. So, we have already said AB is equal to PC here. Let us give them a value which is D. Oh, from this we can say that D is not a unit. Why? Because A is not a unit and B is also not a unit, and therefore, the product of two non-units cannot be a unit, and therefore, D, which is equal to AB, cannot be a unit, and therefore, we have said this statement D is not a unit since A and B are non-units. Now, we have spoken about A, we have spoken about B, we have seen what D is, because D is a non-unit now, but we do not know about C. Suppose C is a unit here, then D is irreducible, and so A or B is a unit. Now, how did we come by this? Because P is irreducible and C is a unit means the product of an irreducible element and a unit is also irreducible. So, which means that either A or B should be a unit here, because PC is equal to AB, and so this will lead to the situation where either A or B is a unit. But this is a contradiction to our original assumption that A and B are non-zero non-unit elements, and therefore, C cannot be a unit, and therefore, C is a non-unit. Now, D is a unique factorization domain, and therefore, C can be written as a product of irreducible elements C1, C2, so on up to Cn, any non-unit. Because C is a non-unit, any non-unit can be written as a product of irreducible elements. A is a non-unit, B is a non-unit, and all these elements can be written as a product of irreducible elements. So, C1, C2, so on up to Cn, A is equal to A1, A2, so on up to Am, and B is equal to B1, B2, so on up to Br. Therefore, let us come here, D is equal to PC, which is equal to AB. I am substituting all these irreducible factors here in this equation. Therefore, D is equal to P into C1, C2, so on up to Cn, and this is, instead of AB, I am substituting these values here, A1, A2, so on up to Am, and B1, B2, so on up to Br. We know that by the second property of the unique factorization domain, that these values are associates of each other. When they are represented as product of irreducibles, they are associates of each other, and therefore, this P should also be an associate of some other element here. And if P is an associate of one of the irreducible elements, let us say A1, A2, so on up to Am, then obviously, P will divide B, because B1, B2, so on up to Br is equal to B. Suppose if P is an associate of one of these irreducible elements B1, B2, so on up to Br, then P should divide A. So, in both cases, we have now shown that if P divides AB, P divides either A or P divides B, thereby proving that P can only be a prime element. So, we started with P being a irreducible element, and we have proved that P is prime. Hence the theorem. The fundamental theorem of arithmetic tells us that the ring of integers is a unique factorization domain. The next theorem states that Z of x is a unique factorization domain. Theorem: every polynomial in Z of x that is not the zero polynomial or a unit in Z of x can be written in the form B1, B2, so on up to Bs, and P1 of x, P2 of x, so on up to Pm of x, product of these terms, where the BI's are irreducible polynomials of degree 0 and the PI of x's are irreducible polynomials of positive degree. Furthermore, if B1, B2 so on up to Bs, P1 of x, P2 of x so on up to Pm of x is equal to C1, C2 so on up to Ct, Q1 of x, Q2 of x so on up to Qn of x, where the Bi's and Ci's are irreducible polynomials of degree 0 and the Pi of x's and the Qi of x's are irreducible polynomials of positive degree, then S is equal to T, M is equal to N, and after renumbering the Ci's and Qi of x's, we have Bi is equal to plus or minus Ci for I is equal to 1, 2 so on up to S, and Pi of x is equal to plus or minus Qi of x for I is equal to 1, 2 so on up to M. The proof of the following theorem was originally given by Gauss. Since the proof is quite long, we will be skipping the proof, but the interested reader can refer to the content for the proof. Let us see some theorems now. Theorem: let f be a field, then f of x is a unique factorization domain. Proof: in the previous module, we have seen f is a field implies f of x is a principal ideal domain. So, by the above theorem, f of x is a unique factorization domain too. Next theorem: if D is a unique factorization domain, then D of x is a unique factorization domain. Proof: we have already proved that Z of x is a unique factorization domain. Similarly, we proved this theorem also. In previous sessions, we had already seen the relation between Euclidean domain, principal ideal domain and unique factorization domain. But in this session, we are going to prove it. Now, the theorem states that every principal ideal domain is a unique factorization domain. The proof: now let R be a principal ideal domain and let A be a non-unit element of R. And therefore, A can be written as P1, P2 so on up to PR, and A also can be written as Q1, Q2 so on up to Qs. So, this is our assumption, and we are assuming that for each Pi and each Qi is irreducible in R and S is greater than or equal to R. So, in other words, so here it is R and this is S, which means that when A is written as Q1, Q2 so on up to Qs, the number of terms or irreducibles are going to be much more here than here. So, A is written in two different formats here. So, since both of them are equal to A, you can write it as P1, P2 so on up to PR is equal to Q1, Q2 so on up to Qs. Both of them are equal to A and therefore, we have equated them. Then in this situation, P1 divides Q1, Q2 so on up to Qs. This is because P1 divides Qj for some j, and this is because R is a principal ideal domain. In a principal ideal domain, we know that every irreducible element becomes a prime element, and this is why we are able to say that P1 divides Qj for some j. So, there is going to be a Qj in one among these elements such that this P1 on the left hand side is able to divide one element here. Let us reorder the elements in such a way that Qj, that particular Qj which is divisible by P1 comes first. So, now we have arranged it and it now becomes Q1. So, Q1 can be written as U1 P1 because now P1 divides this particular Q1, and therefore, Q1 can be written as U1 P1 for some unit U1 of R. Thus, if you are going to write this value here, it becomes now P1, P2 so on up to PR, Q1 is now divisible by P1 and therefore, P1, P2 so on up to PR will become, instead of Q1, I substitute U1 P1 from here and it becomes U1 P1 Q2 so on up to Qs. Let us look at P2 now. P2 again will divide some Qj in this order of elements, and that Qj again you can reorder and put it as Q2, and therefore, because P2 divides Q2, it can be written as some U2 Q2, and therefore, P1, P2, P3 so on up to PR can be written as U1 so on up to Q2 so on up to Qs. And so, you are going to continue this process again and again. So, every time what happens is that there is a P1 here, so they get cancelled. The next time there will be a U2 P2 on the right hand side, and that again P2 will get cancelled. So you can continue this process again and again, and finally on the left hand side all the elements are getting reduced and you are left with only 1. On the right hand side, on the other hand, you will have U1 here, the next time you will have another U2 and so on up to UR. But we have already said that S should be greater than or equal to R. Now P1, P2 so on up to PR will be cancelled on the right hand side, and so you are left with 1 is equal to U1, U2 so on up to UR. But since we have assumed that S is greater than or equal to R, there are going to be some elements, let us say QR plus 1 and so on up to QS on the right hand side, because when we cancel P1, P2 so on up to PR, there will be a U1, U2 so on up to UR left, but still there will be certain elements on the right hand side which cannot be factorized by these P2 so on up to PR, and therefore you will be left with these few elements which are because S is greater than or equal to R. Since Qj is a non-unit for all j, R is equal to S. Now this is not possible because Qj is a non-unit, and therefore R should only be S, R cannot be less than S. That is the only conclusion that we can make here, and therefore P1, P2 so on up to PR are also going to be written as Q1, Q2 so on up to QR. The powers or the suffixes are going to be the same, it cannot be greater or lesser, therefore it is R here and R here as well. And now that we have shown that when they can be written as a product of irreducibles, which is the first part of the unique factorization domain property, so you have shown that you can write it as P1, P2 so on up to PR, which is the product of irreducibles. The second part, you have to show that the factorization is unique up to associates. So now I have shown that this P1, P2 so on up to PR are the associates of Q1, Q2 so on up to QR, thereby satisfying the second property of the unique factorization domain. Now both the properties are satisfied, and therefore we started with R being a PID or the principal ideal domain, and we have now reached a situation where R is also a unique factorization domain. The converse of this theorem is not true, that is, every unique factorization domain is not a principal ideal domain. For example, Z of x is not a principal ideal domain, but we have only recently seen that Z of x is a unique factorization domain, because the set of polynomials in Z of x whose constant term is even is a non-principal ideal. Therefore, it is not a principal ideal domain, thereby proving our statement that every UFD or unique factorization domain is not a principal ideal domain. We may summarize our theorems and remarks as follows. The field implies Euclidean domain, Euclidean domain implies principal ideal domain implies unique factorization domain, and unique factorization domain implies integral domain. So we know that the field is the strongest structure here because it contains both the abelian groups for addition and multiplication as well, and integral domain is the weakest possible structure here. In between you can see that you can remember them in alphabetical order because E comes before P and P comes before U, and therefore this particular order is holding true here, and this is how we have proved all the theorems also. So Euclidean domain, every Euclidean domain is a principal ideal domain, every principal ideal domain is a unique factorization domain, and so on, and we have defined all this with respect to an integral domain only. But the reverse is not true. If you take integral domain, it does not imply unique factorization domain. A unique factorization domain need not be a principal ideal domain, a principal ideal domain need not be a Euclidean domain, and a Euclidean domain need not be a field. So this, in order to prove this, we shall be seeing some examples now. For example, the ring Z of I root 3 is an integral domain but not a unique factorization domain. Z of I root 3 has no zero divisors, that is, Z of I root 3 is an integral domain. Now consider the following factorization of 4. We know that 1 plus I root 3, 1 minus I root 3 and 2 are irreducible elements in Z of I root 3. Now 4 can be written as 1 plus I root 3 into 1 minus I root 3. that is 2 times 2. That factorization of 4 is not unique because you have written it in 2 different ways. The second, the polynomial ring z of x comma y in 2 variables is a unique factorization domain because z of x comma y can be written as z of x into y. However, the ideal I is equal to the ideal generated by x comma y is not principal. Let us prove it by contradiction. Suppose that the ideal generated by x comma y is equal to the ideal generated by p, with p belonging to z of x comma y, then there exist 2 polynomials q1 and q2 belonging to z of x comma y such that x is equal to p into q1 and y is equal to p into q2. As a polynomial in variable y, the polynomial x is having degree 0. Therefore, the degree of p as a polynomial in variable y is also equal to 0. By symmetry, we get that the degree of p as a polynomial in variable x is equal to 0 also, which implies that p is an element of the field f and consequently that x comma y or the ideal generated by x comma y is equal to z of x comma y. But the equality, the ideal generated by x comma y is equal to z of x comma y is absurd. Indeed, the degree of a polynomial xt1 plus yt2 cannot be equal to 0 for any t1 comma t2 belonging to z of x comma y, and therefore 1 does not belong to z comma xy. This is a contradiction. Third, z of root minus 19 is equal to a plus b root minus 19, where a comma b belongs to z and a and b are either both even or odd. Then z of root minus 19 is a principal ideal domain, but it is not a Euclidean domain. The last example, the polynomial ring R of x is an example of an Euclidean domain, but it is not a field. Finally, let us see an application of unique factorization domain, which is the weird dice. This is an application of unique factorization. Let us consider an ordinary pair of dice whose faces are labeled from 1 through 6. So, the probability of rolling a sum of 2 is 1 by 36, the probability of rolling a sum of 3 is 2 by 36 and so on. In a 1978 issue of Scientific American, Martin Gardner remarked that if one were to label the 6 faces of one cube with the integers 1, 2, 2, 3, 3, 4 and the 6 faces of another cube with the integers 1, 3, 4, 5, 6, 8, then the probability of obtaining any particular sum with these dice, called the Sickerman dice, would be the same as the probability of rolling that sum with an ordinary dice, that is 1 by 36 for a 2, 2 by 36 for a 3 and so on. So, I have drawn a picture of a usual die. So, we have 6 faces, it is a cubical structure, the dice we know 1, 2, 3, 4, 5 and 6, and another dice also 1, 2, 3, 4 and 5, 6. So, in order to get a 3, I should get a 2 and a 1. But a Sickerman die looks like this 1, 2, 3, 3, 2 and 4. So, 2 appears 2 times, 3 appears 3 times and 4 appears once, and there is no 5 and 6. The other die will be 1, 3, 6, 5, 4 and 8. So, this is a Sickerman die. If you are going to roll these 2 dice together, it is going to yield the same value as what you will get when you are rolling a usual die twice, or maybe 2 different usual dice. In this example, we show how the Sickerman labels can be derived and that they are the only possible such labels besides 1 through 6. To do so, we utilize the fact that z of x has the unique factorization property. To begin, let us ask ourselves how we may obtain a sum of 6, say with an ordinary pair of dice. There are 5 possibilities for the 2 faces. So, 5, 1, 4, 2, 3, 3 and 2, 4 as well as 1, 5. Next, we consider the product of the 2 polynomials created by using the ordinary dice labels as exponents. So, this can be written as x bar 6, x bar 5, x bar 4, x bar 3, x bar 2 and x bar 1, and when we are rolling the dice 2 times, so it becomes x bar 6, again a product of the same polynomial twice. So, this is why we are writing as this form. Observe that we pick up the term x bar 6 in this product in precisely the following ways, namely x bar 5 times x bar 1, x bar 4 times x bar 2, x bar 3 times x bar 3, x bar 2 times x bar 4 and x bar 1 times x bar 5. So, this is obvious. Notice the correspondence between pairs of labels whose sums are 6 and the pairs of terms whose products are x bar 6. So, it is the same. So, in order to get x bar 6, you get different ways of doing it. This correspondence is 1 to 1 and it is valid for all the sums and all dice, including the Sickerman dice and any other dice that can yield the desired probabilities. So, we are now going to show that the Sickerman die is the only possibility where you will get the same probabilities as the usual dice. So, let A1, A2 so on up to A6, B1, B2 so on up to B6 be a possible way of doing things. So, instead of thinking of these numbers, let us say that there is another pair of dice having certain values on them such that when you roll them, you are going to get the same value as that which you will get when you are rolling these two dice together or an ordinary pair of dice together. But let us forget for the Sickerman die for now. Now, we call them weird dice. Okay? The weird dice will have different values and so on. So, we have two lists of positive integer labels for the faces of a pair of cubes with the property that the probability of rolling any particular sum with these dice, namely the weird dice, is the same as the probability of rolling that sum with an ordinary dice label 1 through 6. You can see that the Sickerman dice, the Cayley table for an ordinary dice as well as the Sickerman dice. But let us come to our weird dice. Using our observation about the products of polynomials, this means that x6 plus x bar 5 plus x bar 4 and so on, you are multiplying them twice and this is equal to some value x bar a1 plus x bar a2, x bar a3, so on up to x bar a6 and x bar b1, x bar b2, x bar b3, x bar b4 and so on up to x bar b6. We have to solve this equation for ai's and bi's. So, if we solve them for ai's and bi's, we will get the answer whether these values can be substituted in the place of the Sickerman die. Now, this is where unique factorization in z of x comes into play. The polynomial is x6 plus x bar 5 plus x bar 4 plus x bar 3 plus x bar 2 plus x factors uniquely into irreducibles as x into x bar x plus 1, x squared plus x plus 1, x squared minus x plus 1. So, this can be written in only this product of irreducibles. Therefore, this equation 1 contains two different polynomials which are identical. We have doing the product of these two polynomials and therefore, 1 can be written as x squared x plus 1 the whole squared, x squared plus x plus 1 the whole squared, x squared minus x plus 1 the whole squared. So, this means that these factors are the only possible irreducible factors of p of x. Let us assume that p of x is equal to x bar a1 plus x bar a2 plus x bar a3 plus x bar a4 plus x bar a5 plus x bar a6. Now, we do not know in which way these irreducibles will have a power. So, let us assume that they have the powers q, r, t and u. So, you will have the irreducible factors are not going to change, but the powers can change. Therefore, you will have x bar q, x plus 1 the whole power r, x squared plus x plus 1 the whole power t, x squared minus x plus 1 the whole power u, where q, r, t and u lie between 0 and 2. They can have the values either 0 or 1 or 2. Let us restrict this further, the possibilities for these 4 parameters. Let us suppose that p of 1 can be written in two ways. So, 1 power q, 2 power r. So, all you have to do is substitute 1 in the place of x. Therefore, you will get in equation 1 particularly. So, you will have 1, 1 plus 1, 1 squared plus 1 plus 1, 1 squared minus 1 plus 1. So, this will become 1 power q, 2 power r, 3 power t and 1 power u. So, the only way that you can get 6 here is if r is equal to 1 and t is equal to 1, no other possibility. Similar way I am doing for p of 0. Here what will happen is, in the place of x you have to substitute 0. So, 0, 0 plus 1, 0 plus 0 plus 1, 0 minus 0 plus 1 and so on. And so, you will get 0 per q, 1 per r, 1 per t and 1 per u. The only way this can happen is if q is equal to 0. On the other hand, if q is equal to 2, the smallest possible sum one could roll with the corresponding labels for a dice would be 3. Since this violates our assumption, we have now reduced our list of possibilities for q, r, t and u to q is equal to 1, r is equal to 1, t is equal to 1 and u is equal to 0, 1 and 2. Let us consider each of these possibilities of u in turn. So, when u is equal to 0, you will get p power x is equal to x power 4 plus x power 3 plus x power 3 plus x power 2 plus x power 2 plus x. Now, if you look at the powers, you can see that they form the secant and die values. So, it becomes 4, 3, 3, 2, 2 and 1, which is the secant and die. The second possibility is when u is equal to 1. Here the labels are x power 6 plus x power 5, x power 4 and so on up to x power 1. Now, this is the possibilities for ordinary die and therefore, you can see that they are the values that you get for the ordinary die. So, 6, 5, 4, 3, 2 and 1 ordinary die. The last possibility is u is equal to 2. Here p of x will have the values x power 8 plus x power 6 plus x power 5 plus x power 4 plus x power 3 plus x power 1. Again they are these values 8, 6, 5, 4, 3 and 1. Once again we get the secant and die. So, we started with a weird die. We thought that it will not yield the secant and die, but we are getting only the secant and die possibilities. Therefore, this proves that the secant and dies do give the same probabilities as ordinary dice and that they are the only other pair of dice that have this property. Conclusion: this is the last session for ring theory and also for this course modern algebra. In all these modules, we gave detailed explanations about group theory and ring theory. We have also covered most of the concepts of algebra. I hope that these sessions enlightened you about group theory and ring theory. Mathematics can be learned by doing problems only. To do problems, please go through the contents in the site. It has some arrangement problems that will help you to sharpen your problem solving skills. I hope you enjoy learning this basic course on group theory and ring theory as much as we enjoyed making this course. We, the Educational Multimedia Research Center, Madurai Kamaraj University, wish that this course helps you to gain academic confidence in algebra, and we hope that this course will serve as a shining beacon and inspire you to learn more about algebra. The thing that counts is not what we know, but the ability to use what we know. We hope to meet you in another mathematical session. Thank you and all the very best.